All right, well, welcome back, everyone. We need to work our way through the rest of chapter 2, I think. Boy, these first two chapters are really long. We've started to get up onto the idea of conformations, and I've given the definition of conformations in the class notes. If I had to define it off the top of my head, I would say conformations are different states of the same molecule. They're not isomers. Your book calls them isomers. I'm sure I mentioned this last time. Your book is wrong on that point. Conformations are not isomers. They're different states of the same molecule, and we're going to start simple. We're going to start with ethane, and these different states arise by rotating around single bonds. In this case, the carbon-carbon single bond. And so one thing you need to know in order to understand this is that freedom of rotation is possible around single bonds. That's something you need to know. So if you did not know that, please write that down. It is possible to rotate around single bonds. Well, unless there's something preventing that from happening, like if it's in a ring, of course, then you can't. But just in an acyclic straight chain compound, generally you've got full freedom of rotation around that single bond. And so that's what gives rise to different conformations. And we could go into quite some depth in conformational analysis. We could start talking in depth about torsional strain. After talking about ethane, we could go into butane and similar molecules and go down all sorts of paths like that. And in 227, we do that. We don't have time to do that here, but I want to give you at least enough of the material so that you can understand the layout and at least get the general idea of how this works. But I would say ethane is about the smallest molecule that you can get that is at all conformationally interesting, that has different conformations. So again, I'll get to you in 1 second. Again, did we already go over intermolecular forces? Yes, we talked about intermolecular forces last time. I'm having a little trouble with the video though. For some reason, last I checked, the video was not compiling. So I might have to make a separate video and put it up on YouTube because for some reason, Monday's class just wasn't working. But yes, we've already talked about intermolecular forces. Everything you need to know in intermolecular forces is in your class notes. I think I've spelled it out pretty well. It's pretty much review from Gen Chem anyway. But yes, I've said all that I'm going to say on intermolecular forces. Remember, we especially talked about hydrogen bonding. That's going to be one of the more important ones. Now there's a question over here. Or was that your question? Conformations are not the same as stereoisomers. That's a good question. And the way you know is because the definitions will be different. We'll define stereoisomers later today, but conformations have a different definition. That's how you know that they're different. Conformations are different states of the same molecule, whereas stereoisomers are different molecules. And we'll get to the definition of stereoisomers later, and we'll do some examples. But conformations only refer to the same molecule. So they're not isomers. And your book does say that conformations are isomers. I would say they're wrong. Conformations are not isomers. So what can we say about ethane? Well, ethane has two major conformations that are available to it. And I've drawn them here using two different ways. These are not the only correct ways to draw them. This way should be more familiar to us, and I'll touch on the important details and make sure you're all clear on what you have to know in order to understand structures like this. One thing that you need to know is how to identify an sp3 hybridized carbon atom. And hopefully you can all do that. An sp3 hybridized carbon atom is a carbon with 4 single bonds attached. That's always going to be the case. There are no exceptions. So a carbon with 4 single bonds is sp3 hybridized, always. It will go to sp2 hybridization if there's a double bond. We went over some examples of that in an earlier class. And it will take on sp hybridization if there's a triple bond or 2 cumulated double bonds, like in CO2. So those are the 3 types of hybridizations as regards carbon. Now other atoms will be hybridized also. Oxygen can take on certainly sp3 and sp2 hybridization commonly. And the way you know about those hybridizations I've gone over in the class notes. So I think I've given you enough information in the chapter 1 class notes so you can know what you need to know about hybridizations of various kinds of atoms. It's something you would have gone over in Gen Chem, and I'll be happy to talk about it at any time during office hours. So you need to be able to recognize sp3 hybridized atoms. Hopefully you're recognizing that both of the carbon atoms in ethane are sp3 hybridized. So far so good. Is everyone following me? Okay. So that's why I'm showing two things. First of all, I'm trying to show bond angles of around 109.5 degrees. So that's going to be the predicted best angle, best bond angle for 109.5 degrees. And that's what I'm trying to do here. In order to show that, I must use wedge and dot bonds. Your book goes over them, your book goes over how to draw them, but I would hope they had been introduced in Gen Chem. If not, it's okay. If not, then this is what wedge and dot bonds look like. And we use them to indicate generally sp3 geometry. Oh, wait a minute, I think I remember. There might be a problem with my mic. First of all, if everyone would check in terms of attendance. I think I had to change to real. There, that might be better for, oh, it was good. Is this worse then? Those of you in chat? That was worse. Okay, we'll go back to the other. I can handle that. Good, so please register your attendance. You'll just get 10 out of 10 attendance points for today. Do we have to purchase a resubscription? Yes, we are sometimes going to use polling. The good news is at least that's significantly cheaper than a clicker unit. So yes, I'm afraid so. Today we're not using polling, but we probably will on Friday, and I usually will at least once a week. I'll try for twice. Good, so getting back to the wedges and dots, the wedge bond means that it's coming out of the plane at you. And that's what this is trying to show, that this hydrogen is in front of the plane and the bond to it is sticking out of the plane. Meanwhile, the dotted bond means that the bond is going behind the plane. And the same thing over on the other side. And I think you'll agree, I don't know why that bond has to be so wavy, we can fix that. I hope you'll agree with me that I've at least put forth a reasonable good faith effort at showing all these bond angles as being 109.5 degrees. By bond angles, I mean that I want to make sure that I explain what every single thing means so that everyone knows what you need to know. By bond angles, I mean that you're going to start on one atom and then count another atom and then a third atom. 1, 2, 3, that angle that describes. So 1, 2, 3. Do you see how I did that? That's an example of a bond angle. All of those need to be 109.5 degrees. That's what the VSEPR model predicts for sp3 hybridized atoms. And so that's why I'm using wedges and dots here. And so one thing that you need to know is that when you're showing sp3 hybridized atoms using the correct geometry, which you don't have to, you could also, I'll go back to the bond angle. So I'm going to start at this H over here, just as an example. 1, 2, 3. That's an example of a bond angle, that angle that describes. Do you have to have the bond angles memorized for sp3 being 109.5, sp2 being 120, and sp being 180? Those were covered in Gen Chem. So yes, I expect you guys to know those. I've also listed those in the chapter 1 class notes, so it says there what you need to know. But yes, I do expect that you know those, at least the theoretical bond angles in those three. Now, in any real molecule, these angles aren't going to be exactly 109.5. Let's find another example of a bond angle. 1, 2, 3. And that also, you see how it's a good deal more than 109.5? So, I'm sorry, a good deal more than a right angle, right? You know a right angle is 90 degrees. So it's a good deal more than that, obviously. And that's what I'm trying to show. And the idea that I'm trying to get across is that when you're drawing sp3 hybridized atoms in the correct geometry, you might not have to draw it in the correct geometry. It depends what the question asks you. Sometimes OWL will ask you to use the correct geometry. Other times it'll say, don't worry about that, just draw a flat structure. But one thing that you need to know, again, I'm trying here to be as clear as I know how to be, in terms of making it clear what you need to know. I'm really trying hard here. You need to know that whenever you're showing an sp3 hybridized atom in the correct geometry, you must use wedges and dots. You must. So in that case, you must do it. If you're just drawing a flat structure, don't bother. And the question will make it clear what you need to do. Owl's usually, not always, but usually pretty good about that in terms of exactly what you need to do to get credit. Okay, so this is one possibility. And I think you can see that in this case, it's this part of the molecule, this HCCH over here, that all lies in the same plane. The way I know that is because all of those bonds are just straight lines. So all of those lie in the same plane. That's one possibility. That's one conformation. Here's another conformation. Here, it's this part of the molecule that lies in the same plane. We've turned around that angle, as it turns out, 60 degrees. I should say we've turned around the carbon-carbon bond 60 degrees, as it turns out. So these are the two conformations of ethane. This one is called the staggered conformation, and this one is called the eclipsed conformation. And the reason for that is that in the eclipsed conformation, any two hydrogens any hydrogens on the two carbons that are in corresponding places, like these two, and also like the two on the dotted bonds, are directly right in front of and behind each other, just like the sun and the moon, or the moon and the Earth's shadow in a solar or lunar eclipse, respectively. I think I got that right. Good. So these two conformations are different. They're not isomers. They're the same molecule. All we've done is rotate around that single bond. So they're not isomers. Isomers is always going to refer to different molecules. These are the same molecule. So that's one way to show it. And there are others besides these two. This is another way to show what you're seeing here. This type of drawing is called a Newman projection. And in a Newman projection, what we're doing is we're putting our eyeball right up against that carbon-carbon bond, and we're looking right down the bond so that this carbon lies directly behind that one. And I think what you'd see is this hydrogen over here, for instance, winds up over here. It's pointing up. This hydrogen's pointing up, that hydrogen's pointing up. And the other two hydrogens on the same carbon are over here. And again, one is sort of coming out at you and the other is going into the plane. That's the dot bond, the wedge bond and the dotted bond, respectively. So, and then you can see these three hydrogens on the back carbon. We try to show that they're on the rear atom by kind of breaking up these lines with this circle. That's how that's done by convention. So I tried to color code it. These three red hydrogens are these ones that are in back, and that's what the staggered conformation looks like. And the eclipsed conformation would look something like this. It's kind of always awkward to draw the eclipsed conformation. Just got to do the best you can. So, but you can see that the pairs of hydrogens are directly in front of and behind each other. And that's going to cause an increase in energy, as you might imagine. The carbon-hydrogen bonds are getting in each other's space. And what do we find in bonds but electrons? Electrons are negatively charged, and like charges repel. So the molecule would rather adopt a conformation in which that problem is relieved by the hydrogens not being directly behind each other. So the staggered conformation is going to be more stable. Actually, let me do both. It's more stable, and it's lower in energy. Sorry for my handwriting. And the eclipsed conformation turns out to be less stable, and therefore higher in energy. H-I-G-H-E-R. In energy. So that's another set of principles that you learned in Gen Chem, but are worth reviewing. Higher energy means lower stability, and lower energy means higher stability or greater stability. Higher energy means lower stability, lower energy means greater stability. That's always the case. There are no exceptions. You don't have to worry about any exceptions. It's always true. So, and again, the reason for that is in the eclipsed conformation. I'm going to try to come up to the camera here and show you guys my little tinker toys. let me make sure I can line that up right. Except, you know what I need to do? I need for chat to change to viewing the screen as opposed to viewing the whiteboard, or they won't be able to see it. There we go. And I'll even maybe make that a little bigger, just for science. So here's our ethane molecule. Let me see if I can get it on the camera. Yep. And now let's look down that carbon-carbon bond. Whoa. Good, there we go. So that would be the eclipsed conformation. You can see how each hydrogen in front has another hydrogen directly behind it. But if we turn around that bond by 60 degrees, do that a little better, then we're in the staggered conformation. And you can see now no hydrogen is directly behind or below, or directly behind or in front of any other. I'm sort of holding it by this hydrogen in front. Do you see how we got rid of that problem of the hydrogens being close together in space? And again, that phenomenon happens to be called, what's the word I'm looking for? Torsional strain. Like I said, we can get very deeply into the weeds if we wanted to. I just want to give you the basics so that you understand. Again, the reason we're doing this is we need to learn what organic molecules are like. We need to get away from memorizing pictures and just memorizing things and not really understanding how these things work. And this is part of how organic molecules work, is understanding that you've got full freedom of rotation around single bonds, in acyclic molecules anyway, and that can lead to the possibility of different conformations. Ethane is the smallest molecule for which we even get different conformations, I think. I can't think of anything smaller than it that does. Good, so I think that's probably all I need to say about ethane. Let me go back to my whiteboard. Let's get this out of the way. Okay, so, and these are not the only ways to show the two different conformations. These first drawings are just kind of standard structural drawings with wedge and dot bonds. That's nothing new. We've seen those before. These things here are called Newman projections, and they're just another way of expressing the same thing. Neither of these is any better or more right or safer than the other. They're both fine, and there are other ways besides this to show this distinction. So with that, I think that at least helps us to understand what conformations are. Again, I've given the definition. Conformations are different states of the same molecule that arise just by rotating around a single bond. And they'll generally be different in energy. So they are not isomers, in spite of what the book says. The book is wrong when it says that conformations are isomers. And I double check with a few of my colleagues just to make sure I'm not losing my mind. And well, okay, well, fine. Obviously, I am losing my mind. But in spite of my losing my mind, I'm still right about that. My colleagues still agree with me on that point. Good. So that gives you at least an idea of how conformations work. And we could apply this same type of thinking to any number of other molecules besides ethane. There are lots of other molecules that are essentially the same as ethane in terms of having two isomers, there I go, two conformers, one eclipsed and one staggered. And you can get any one of them by replacing any one of these 6 hydrogens, doesn't matter which because they're all the same, with pretty much anything you want. You can replace it with an OH and now you've got ethanol. You can replace a hydrogen with a chlorine, now you've got chloroethane. You could even replace an H with a methyl group and now you've got propane. And all of those molecules are the same exact idea as ethane in terms of their conformations. They will have 2 conformations, one will be eclipsed and one will be staggered. The only thing that will differ between all the above molecules is the difference in energy between these 2 conformations. As I recall, for ethane, the difference in energy is something like 12 kilojoules per mole. I certainly don't expect you to know that. You know me, I'm not usually a big fan of people memorizing numbers. But the other molecules would just have a different, it would not be 12, it would be some other number. in terms of the difference in energy. But you would still have two conformations, one staggered and one eclipsed. Good, so I think that's good enough for ethane. Everyone registered their attendance, whether in chat or in person? Please and pretty please. Good, any questions then on ethane? Well, I think the question is that the only possibility for ethane? And I think if you find, I think those are the only two conformations. There are other correct ways to draw them that involve turning, but they'll be equivalent to one of those two. That's not your question. All right, let me try again. Sorry.
Yeah, it's like that. Can we change that the dots on that hydrogen on second carbon?
I would want to keep the bond angles about like that. So you're saying, can you change the wedge and the dot ones on the second carbon? I wouldn't. I'm still not answering your question. I think you're asking about the H's on the second carbon. And you're saying, would it be okay if you switched the wedge and the dot, you'd rather they be switched? I think not. I think that's correct. I think that's better anyway. And the way you can tell that it's better is because both of the wedge bonds are closer to the center of the molecule. Do you see what I mean? That will help you to see that it's right. But as far as I know, that's the best way to do it. I think so, yes. Isn't that the same in this one too? The two wedge bonds are closer to the middle. The two dotted bonds are further away in that case. I'm trying to show kind of a plane of symmetry there. So that's the logic behind it. This isn't a majorly big deal. You know, the other way I don't think would be, I'll get to you next. The other way I don't think would be 0 points. If it were kind of like that on OWL, I would at least hope they would give you some credit. But I do believe those are the best ways. Something like that. And the thing that you're aiming, I don't want you to just memorize the picture, but you're aiming for 109.5 degree bond angles. Obviously, I'm not going to get out a protractor and measure it. You know, but that's what you're aiming for. And I think you'll agree I did a pretty good job at kind of getting close to that. Yes? Oh, okay, good. I read your mind. All right. Are we finishing chapter 2 today? God willing, and the creek don't rise, we will finish chapter 2 today. Yes, at least I think today is going to be all the talking I'm going to do on chapter 2. And I can never get to absolutely every topic, but I spend the time on the things that in my experience need the most explanation. So having done with ethane, let's now move on to cycloalkanes. And again, in terms of naming them, it's pretty similar to naming alkanes. I would say if you know how to name alkanes, you know 95%, at least maybe even 97 or 98% of what you need to know in order to name cycloalkanes. There's a lot of overlap. The only difference between cycloalkanes and alkanes is the obvious one. Cycloalkanes don't have a beginning and an end of the chain. So you're not going to be numbering from one end of the chain to the other because there's no ends. Right, it's all together. So numbering in cycloalkanes is a little different, but it's not entirely different. I thought the mic just went out. Are we still good in chat? Can you still hear me? Oh, good. Okay, I thought it went out. All right. So I think that you can pretty much practice on your own. Let's move on then to cycloalkanes, and I want to deal with the smaller cycloalkanes first. They will be cyclopropane, cyclobutane, and cyclopentane, which, as the name implies, have 3, 4, and 5 carbons respectively. And we're going to be able to dispatch them pretty quickly. There's not a whole lot to say about them. I think you'll agree with me that the smallest possible cycloalkane has to be cyclopropane. You can't have cycloethane. You have to have 3 carbons to make a ring. And so the cyclopropane molecule has 3 carbons connected thusly. And I think you'll also agree that of necessity, that molecule is the shape of an equilateral triangle. It has no choice. It can't be anything else. And so there's 3 CH2s, so the hydrogens are still there, of course, connected into the shape of an equilateral triangle. Now we've got a significant problem with cyclopropane. We talked about bond angles. What about this angle? Well, you know, high school geometry was roughly 600 years ago for me, but even I can remember that the angle in an equilateral triangle is 60 degrees, right? And we don't want 60 degrees. We want it to be 109.5 degrees, or as close to that as we can get. So I think you'll agree 60 degrees is way off from 109.5. As a result, the cyclopropane molecule is exceedingly strained. Strained meaning higher in energy. Strained means higher in energy or less stable. And that loss in stability is because this bond angle is very, very far away from the ideal of 109.5 degrees. We call that type of strain angle strain. You can also call it ring strain. These things have names. You know, and we could go nuts with defining 10,000 words here. But my point here is I would expect you to see that this molecule must be in the shape of an equilateral triangle. It has no choice. The molecule must be planar. At least the 3 carbons in it are planar. It has no choice. There is no other possibility. And as a result, that's really bad. It's very, very unstable. If you can get that from it, you're doing pretty well. That's really all we have to say, I think, about cyclopropane. What about cyclobutane? Well, it's tempting to draw it as a square. And certainly if you're just drawing a flat structure, that's fine. As a matter of fact, cyclobutane is not planar. So this angle here, these aren't right angles. They're actually a little bit more than 90 degrees. I forget if they're 94, 95 degrees, somewhere around there. They're still nowhere. I'm gonna go, let's see, 94 degrees question mark. You know, I don't know if that's exactly right. You can check me on that. But they're still pretty far from 109.5, better than 60, but still a good deal of angle strain in cyclobutane. But again, this molecule is actually not planar. It puckers out from planarity a little bit, just to try to increase those bond angles a little bit. But there's only so much we can do. When you put in a 5th atom and you go to a 5th carbon and you go to cyclopentane, now things are finally starting to look up again. So cyclopentane is 5 carbons, and cyclopentane has almost no strain in it. Still a little teeny bit, but not very much. Most of the angle strain is gone. Cyclopentane, in fact, is also not planar. One of the carbons sticks out a little bit. It looks kind of like an envelope. But there's very little strain in cyclopentane. We're maybe not quite at 109.5 degrees, but pretty close. I think it's maybe 106 or 107 or something like that. It's pretty good. It's pretty close. Things start to get real when we get to cyclohexane. That's what we're going to get to next. We'll probably spend the rest of the class on cyclohexane, which again, you can draw like a hexagon. It's not wrong. But cyclohexane is not planar either, and I have my little models there ready to help us understand that. So please don't confuse cyclohexane and benzene. Benzene and cyclohexane are completely different critters. Don't just memorize their hexagon things. They're totally different. Cyclohexane is a saturated compound. It's a cycloalkane. Benzene's a different critter. Benzene's an aromatic compound. So don't just memorize shapes or memorize pictures. These things have to mean something to you for best results. Oh, good. So really, there's not a whole lot else to say about the small cycloalkanes, except for one small thing I want to talk about, and that's this whole business of cis and trans geometry with cycloalkanes. It gives rise to stereoisomers. So now we're going to get our first taste of stereoisomers. We'll get a lot more of that when we get to alkenes. That also has cis-trans possibilities. Actually, some of you have already asked me about cis and trans and alkenes, which is really good. We'll get to that. I think that's chapter 3. And then we also need to get to the notion of chiral carbon atoms, left and right-handed sp3 hybridized carbon atoms. That'll come along later as well. That's also another type of stereoisomerism. But let's, I don't know, I could take really any of these. I'm just for fun going to take cyclopentane, and I'm going to kind of turn it on its side. See how good my artwork is today. I'll even bold these in just to improve the illusion. I think cis and trans are in chapter 2. Well, it is. This type of cis and trans is in chapter 2. The type that refers to cycloalkanes. So that's why I'm about to cover it, because it's in chapter 2. Cis and trans alkenes are in 3. And the other stuff, I think, is in 4 or 5. So let's consider 2 different isomers of 1,3-dichlorocyclopentane. This is one of them. And the other one would look a little something like H over here. Just trying again to bold this a bit, just to make it look like it's popping out at us a little. Chlorine over here. This hydrogen still over here. And this chlorine still down here. Okay, so those are the 2 possibilities. And I think you will agree with me 2 things, at least I hope you will. First of all, these 2 molecules are different. In this case, the 2 chlorines are on the same side of the ring. They're both below, or we could turn the molecule over and they'd be both above it. It would be the same compound. Meanwhile, with this one, you've got one above and one below the 5-membered ring. So those are different compounds and they're not interconvertible. You can't turn one into the other by rotating around single bonds because we're limited in how much we can rotate because it's a ring. You know, you can't rotate all the way around without breaking any bonds. So those 2 are permanently different compounds, and that's an example of stereoisomerism, or we would say that they are stereoisomers. And I've put the definition of stereoisomers in the class notes, but I would say that stereoisomers differ from constitutional isomers. We said that constitutional isomers are compounds with the same molecular formula, but the atoms are connected differently. There's different types of bonds in the 2 molecules. With stereoisomers, they have the same molecular formula, and the atoms are connected the same way. They have all the different types of bonds, same types of bonds, the same number of carbon-chlorine bonds, same number of carbon-hydrogen bonds, and so forth, these 2. But the atoms are arranged differently in 3-dimensional space. So that's what we mean by stereoisomers. And there are multiple flavors of stereoisomers. This is the chapter 2 flavor of stereoisomers. We'll get to another flavor in the next chapter and yet a 3rd flavor, I think, further down the road. For now, it's enough to see that these 2 compounds are different, and so they need different names. We can't just call them both 1,3-dichlorocyclopentane, but we would call the first one cis 1,3-dichlorocyclopentane. Dichloro, HLORO. That's this one, cyclopentane. Cyclopentane because the ring has 5 carbons in it. 1,3 because wherever you start counting, the shortest way around to get the lowest possible numbers is 1, 2, 3. If you go the other way, you'll get like 1, 2, 3, 4. So stereoisomers are the same atom-to-atom bonds, but what makes them isomers because they're arranged differently in 3-dimensional space. Here, these 2 chlorines are on the same side of the ring. Here, one's on one side and one's on the other. So that's that one. This one over here, we would have to call trans 1,3-dichlorocyclopentane. And they are indeed different compounds. They will have different properties, and they could be separated fairly easily. So we use cis to mean they're on the same side of the ring, trans to mean they're on opposite sides, dichlorocyclopentane. Chat, you're in the way. And that's not just true of cyclopentane. I could have used cyclopropane, cyclobutane, cyclohexane. I could have used any cycloalkane. that the definition of cis and trans is the same regardless of the ring size of the cycloalkane. This also brings up another thing, at least in my mind, and I'm sure a lot of you are wondering as well. Well, what can we go past cyclohexane? Certainly, cycloheptane, cyclooctane, cyclononane, those are all things, those all exist. But actually, as you get the rings larger than cyclohexane, you start to introduce more strain back in, because it seems no matter what you do, the thing can't avoid bending around such that some carbon bumps into some other carbon as you get to larger rings than cyclohexane. So cyclohexane's special. Cyclohexane is no angle strain. All of the bond angles are exactly 109.5 degrees. And as a result, it's got a number of other interesting properties, which, God willing, the creek don't rise, as I like to say. We will get through as many of them as we can in the next 15 minutes. But things start to get interesting with cyclohexane. Good. Any questions then on the smaller cycloalkanes? You can do that also. It's not wrong. I'll show you how that would look. If you wanted to use wedges and dots to show the chlorines over here, in the first one, you would say both of those chlorines are pointing down, right? So you draw dotted bonds. Oops, Cl, sorry. Or in fact, if you drew them both as wedges, it just means you turned the molecule over. It's the same thing. Both would be accepted. Both would get full credit. What about the other one? Well, you'd need to make one a wedge and one a dotted bond. Looks to me like this one's pointing down and that one's pointing up. And you'll notice that I didn't show the hydrogens, so you can draw your own conclusion as to whether not showing those hydrogens would lose points, right? You can if you want to. It's just they're assumed if you don't. So those are also perfectly good ways to draw the same molecule. Any of the above would get full credit. Is that kind of what you're asking? Any of the above would get full credit. But now let me ask you this. Regardless of what the question is, what now if we just drew straight lines? Well, I think you'll agree this needs to lose at least part of the credit, right? Unless you're only talking about connectivity, because that doesn't make it clear which of the structures you're talking about. The reason this is different from that is because on this one, I'm being very careful to show 3 dimensions in the way I've drawn the ring. This is different. This doesn't show 3 dimensions at all. So all of those are fine. This is not entirely fine. Unless the question, I suppose, were 3-dichlorocyclopentane and don't worry about stereochemistry. Then it would be fine. So all of it depends on how the question is phrased. You need to watch owl like a hawk. So we should either shade the ring or the line. Yes, any of these would get full credit. Any variation on that would get full credit. Other questions then? Well, except insofar that you're not really going to be shading anything for me, right? You're just going to be picking A, B, C, D, or E, something like that. But anything like that should get credit on OWL. And if it doesn't, that's why you only need to average 70%. Yes? In other words, whether both wedges or both dots, no, there would be no reason to select one or the other. They're the same thing. So either one would get full credit, which means that to me, they're the same, and you guys just need to practice until you see that they're the same. They're not different things. What I was afraid you were going to ask, is what if we changed this dot to a wedge and that wedge to a dot? That's what I was afraid you were going to ask. Welcome to Well, I can't even remember words right now. Welcome to enantiomers. We will get there later. That's a few chapters down the road. Good. I mean, these are good questions, but let's move on to. And did everyone register their attendance? I'm just. Why can I not see it? There it is. I'm just double checking the little thing that says we're recording, which it said it on Monday, so I don't know what happened. But unless I can somehow recover Monday's class, I'll need to just make a separate video, which I would want to do anyway. I would like to the full set of videos. So be that as it may, let's move on then to the big kahuna, cyclohexane. So cyclohexane is a saturated six-membered ring. Saturated means it contains as many hydrogens as it possibly can. There's no way to stick more hydrogens on without violating the octet rule. And cyclohexane is not planar, but in its most stable form, it adopts a puckered conformation looking something like this. We call that a chair conformation. And I have tinker toys to show you as we get closer to the end of the class. And I guess the idea is that you can put your butt over here, your legs will go down over here, and you can lie back with your head over here. So they call it the chair conformation. By convention, we don't use wedges and dots when we're drawing cyclohexane chairs, but we do need to be careful to get the correct bond angles. And boy, I am rusty. It's been a year since I've done this. Yes. So we'll just start with unsubstituted cyclohexane, just C6H12, H over here, H over here, H over here, H over here. H, H. And my criterion in all cases, I'm aiming for 109.5 degree bond angles. H up here, and H over here. H over here, trying to make this better. There we go. So there's your cyclohexane, C6H12. And one thing that I hope comes out almost immediately is that I think you can see that there's 3 hydrogens that are sticking straight up and 3 that are, wait a minute, here's 1, 3 that are sticking straight down. So you got straight up and straight down. The chair conformation, yes, it is. It takes practice to draw chairs, but it's worth your trouble, I think, because cyclohexane rings show up a lot in all kinds of natural compounds. So, I think it's time well spent. And again, you're never going to be drawing any actual chairs for me on exams. I think you'll need to be able to do it to get the questions right, but I'm not grading your structures directly. So it's good and it's bad having multiple choice exams. Anyway, you've got 3 that are sticking straight up and 3 that are sticking straight down. Let me color them, I don't know, green. So this one and that one are sticking straight up. Likewise, that one and that one are sticking straight down. And all of those ones that I circled, we call axial positions or axial hydrogens. And of course, they don't have to be hydrogens. We can and will replace them with other groups shortly. And the other ones, the ones that are sticking out at the periphery of the ring, or if you will, around the equator of the ring, we call those equatorial positions. And you'll notice that every carbon atom has 1 axial position and 1 equatorial position, always, no exceptions. And another thing I think you'll notice is that they alternate. The axial goes from straight down to straight up to straight down to straight up. And actually the same thing happens with the equatorial. This is sticking a little bit up, this is sticking a little bit down, this is sticking a little bit up. So up and down alternates as you go around. It's just the nature of the structure. That's just how cyclohexane works. And here comes the fun part. This chair conformation is in equilibrium with another chair. And this really is an equilibrium now. This is not resonance. This really is flipping back and forth. Let me number these carbons, maybe in yet a different color. so that you can see what's going on. Well, just for fun, we'll call that carbon 1, 2, 3, 4, 5, 6. And this is what happens when the cyclohexane undergoes what's known as a ring flip conformational change. Ring flip does not mean that we take the thing and flip it over like a pancake. It's a conformational change involving all 6 carbon atoms. And basically what we're going to do is we're going to grab this carbon and pull it up, and grab this carbon, carbon 4 in this case, and pull it down. We'll just invert the whole molecule. And as a result, carbon 1 is going to wind up over here, then carbon 2 over here, 3, 4, carbon 5 will be over here, and carbon 6 will be over here. We'll just bend the whole thing around. And like I said, probably right before I go, for my last trick, I'll show you how that looks on a model. And as a result, whoops. Well, let me just first draw in the 12 hydrogens, and then we'll look at my model and we'll see if we can make some sense out of what just happened. But I think you'll notice something intriguing. At least I think it's intriguing. I hope you guys like it too. And again, the criterion I'm using to decide where I'm going to put my H's is I'm aiming for bond angles of 109.5 degrees. That's always my criterion. Good. So, let me get in your face literally. So here's my model of, oh, except I have to switch to screen again for the people in chat so they can see it. And I'll put the whiteboard back up again before we leave, but for now, we need, oh, you can see without the switching, really? I did not know that. Well, that in turn will make it easier for the people in the classroom. You don't want to look at me, you want to look at my model. Good, ooh, except if my stupid big hand's in the way. Okay, oh, you can switch it yourself. Well, that's nice to know. Gosh, you guys are better at this technology than I am, that's for sure. At least some of you are. Good, so here's my cyclohexane. And what I've done is I've made the axial hydrogens green, going straight up and straight down. And as I said, in a ring flip interconversion, I'm going to grab one end and pull up and grab the other end and pull down. Nothing up my sleeve, my hands never left my arms. But that's the nature of the ring flip conformational change. Oh, except you can't see. Other than that, it would be fine. So I'm just going to grab over here and pull up, and grab over here and pull down. That's the nature of the ring flip conformational change. Focus. Thing is trouble focusing. Anyway, I'll show you that hopefully on camera a couple more times. So that goes back to where we started. And here you go to the ring flip conformation. So with my hands not leaving my arms and nothing up my sleeve, I have a short sleeve shirt anyway, what do you notice happened when we did the ring flip? What happened to the axial and equatorial positions? They switched, yes. And that actually represents physical reality. That actually does happen. When on your homework, you're going to get to deal with some cyclohexanes that are substituted. And one thing that you're going to need to know is if we replaced any of these hydrogens, let's say with a methyl group, it could be anything. It's better for any other group to be in an equatorial position than in an axial position. Because in the equatorial position, it sticks away from the ring. And so it doesn't bump into other groups as much. If instead, like let's say we swap this position with something big, now it's bumping into these guys all the time. So that's why, other things being equal, it's less energy, it's more stable for other groups to be in the equatorial position than in the axial position. And that's going to be the main thing that you'll need in order to work out, like comparing two different ring flipped forms. Now, of course, I don't expect you to memorize any numbers. I really don't care if you know how many kilojoules per mole higher in energy it is for a methyl to be axial and equatorial. Of course not. I don't know off the top of my head myself. I would never ask you to memorize that. But that, I think, will at least get you started. I mean, I could certainly say more, but I think it at least gets us in a good spot to start chapter 3 on Friday. If I have to say a little more about cyclohexanes, that's fine, but I think that will at least get you started. So other than that, I'm out of time, so have a great day. We'll see you Friday.